And we're looking at 4.2 here. So here is a quick check for prior knowledge for you to complete. A, within the context, what does it mean for an object to do work? And then B, what are some ways that a pitcher can throw a baseball faster? Some techniques, some methods, so on and so forth. It can be physics-based or it cannot be, or it can be non-physics-based, just for time being. Perhaps you're familiar with baseball and are aware of some ways that you can do this, okay? Let's take a moment to answer this and then we'll move on. So 4.2, the work-energy theorem is what we're looking at today, okay? So some announcements. There's no immediate announcements. Again, please have a great Thanksgiving, save me some turkey, and a slice of pie, okay? So what we're up to today, what is work and the work-energy theorem? How is energy converted to one form from another? And how can we mathematically model such scenarios where energy is being converted from one form to another? And then what are some applications of work and energy to real-world scenarios, or scenarion, as I spelled right here apparently. So let's take a look at what work is, okay? So as we saw in 3.1, energy can be transformed or moved from one form or place to another. Like we saw with our car example, gasoline releases chemical potential energy that's converted in the engine to kinetic energy, allowing the car to move. Better said, first it's converted into heat, and then that heat is converted into kinetic energy that allows us to move, okay? So what causes this change in energy is that we have a force that's applied over a distance that causes a change in energy to occur, okay? So, for example, inside of a car engine, there are pistons, and what the pistons do is they compress the car, compress the gas compress the gas that's ignited inside of the engine. And so those pistons do work. They apply a force over a distance, which allows chemical potential energy and heat to be converted into kinetic energy, okay? So a force applied over distance will cause a change in energy to occur. Another way to think about that is that if you push on a car or you push on an object, that object is going to gain more energy the more you push on it and the longer distance for which you apply that force over. AKA, if I push on a crate over a certain amount of distance, it'll speed up a certain amount, but if I push over a longer distance, the crate will speed up even more. So a force applied over distance causes a change in energy to occur. Now the big thing is that this force must be in the same direction as motion of our object. Otherwise, if it's acts, say, perpendicular, or it's not acting in the direction of motion of our object's not going to speed up because we require force in the same direction as we're moving to cause a change in motion. So force must act in the same direction as our motion. So, for example, a car motor must act over a distance to cause above action for a car to begin moving. Let's just say, it's good just right here. So let's take a look at some examples here, in which the cases below is work done, okay? So in this case, let's suppose we're applying a force, but it's not causing a motion to our box. So maybe our box is on a real rough surface with a lot of friction. And then let's say in this case, our person is walking to the right, but the force they're applying is perpendicular to lift up their box. So in the first situation, a force is applied, but the box does not move. So work done by the person is zero. The force must act over distance. Again, we can think about this in terms of the box is not moving as a result of this force, so our box is not acquiring any energy. No, it's not acquiring any kinetic energy specifically. And then in the second case, the force acts perpendicular to the direction of motion and thus has no effect on the motion of the object. So no work is done. In this case right here, we continue to move at a constant velocity, so our energy remains the same. Our energy is not changing here, okay? And work causes a change in energy, okay? So the force in this case is just responsible for uplifting our object. It's not responsible for causing our person to walk forward. So no work is done in the second case either. So we capture all of the above, the idea that work causes a change in energy, that force acting over a distance causes a change in energy, by the work-energy theorem. So work-energy theorem states that an external force applied over a distance can change the kinetic energy of an object, or work equals change in kinetic energy. Okay? So work equals change in kinetic energy. So because work shares an equal sign with the change in kinetic energy, the unit for work is joules, J. Okay? And so this actually explains why a baseball pitcher, if any of y'all play baseball, one of the main ways that person's advised to speed up a pitch to throw faster is to throw with a longer stride. The reason being is that if you throw with a longer stride, you're increasing the distance over which the force you apply to the baseball acts, and thus you're applying a force over a longer distance. You're doing more work on the baseball, which has caused a greater change in kinetic energy. So let's take a look at some examples here, okay? A 0.026 kilogram bullet has a muzzle velocity of 335 meters per second when it strikes a piece of pine board. After striking the pine board, the bullet penetrates 0.019 meters before coming to a stop. What is the average retarding force exerted by the wood on the bullet? So the key to these work energy problems here, okay? Let's see here. All right, so the key to the work energy problems right here, okay, is first off, you need to write down the information that you know, okay? Oh, backed up too much here. We need to write down the information that we know, okay? We need to determine the variable that we're looking for, and then we're going to plug in the known information and solve for the unknown information, okay? So we know that our bullet is going to strike the board at 335 meters per second, okay? So that's going to be our initial velocity. All right, we know the bullet's coming to a stop, so we know our final velocity is 0. We know that the distance traveled is going to be 0.019 meters, and we know the mass of the bullet is going to be 0.026 kilograms, okay? So in this case right here, we're going to be working with the work energy theorem. We need an equation that relates force and distance, okay, to a change in energy. So we're going to have force times distance equals change in kinetic energy. Now in this case right here, I'm going to have a negative sign. The reason being is that this force is a retarding force, aka it's stopping our bullet. So if our bullet's going to the right, that means our force must be acting to the left to slow us down, okay? So we're going to have negative force times distance equals change in kinetic energy, or Kf minus Ki, okay? So now what we can do is we can substitute into our equation. So Kf is going to be 1/2 mvf squared. That's our final kinetic energy, so it's going to be 1/2 mass times our final velocity squared, minus 1/2 times our mass times our initial velocity squared, okay? So as a result, okay, we can start by recognizing that our final velocity is 0. So that means our final kinetic energy is 0 because we have no motion. So we can cross out this term right here, okay? So we're going to have F average times D equals minus 1/2 mvi squared. We have a minus on both sides here. We have a minus on the left side and a minus on the right side. So we can cross out both sides to give us F average times D equals 1/2 mvi squared, okay? So now what we can do, all right, is we need to solve this equation for F average. So we can divide both sides by D. Since D is a variable, we can divide both sides by D, and we can get F average equals 1/2 mass times initial velocity squared divided by D. So now at this point, we can plug in our known information. Again, the mass is going to be 0.026 kilograms. The velocity, the initial velocity is going to be 335 meters per second squared. And then the distance traveled is 0.019 meters. So D gets replaced with 0.019 meters, okay? So that tells us when we put all this into our calculator, the average force that our board has to exert is about 77,000 newtons, okay? So let's do an on our own example here, okay? Top Thrill Dragster has a 200 kilogram roller coaster car that can speed up from rest to 52 meters per second over the course of 300 meters. What must be the force exerted by the launch system to attain this? All right, so one way we can use the work energy theorem is to figure out the distance required in order to reach a certain speed given a certain force acting. So we could combine units 1 and 2, or better said units 2 and 3, with kinematics and dynamics to figure this out. All right, we could figure out that if it's going to be over 300 meters, we could figure out the acceleration using kinematics, and then we could figure out the force using dynamics. But that is a little bit cumbersome. So the nice thing is that the work energy theorem actually allows us to combine change in kinetic energy with, the work energy theorem allows us to take change in kinetic energy with force and distance, and that allows us to combine dynamics and kinematics into one single concept. So we don't have to do kinematics and dynamics together here. We can combine them through the work energy theorem and just focus on strictly using one equation. So let's see what the top thrill dragster looks like then in person. I'm not connected to the internet. Uh-oh, that's not good. Let's go ahead and get me connected. And we'll go ahead and watch this guy take off and see the work energy theorem in action. Inception. What is this playback going on? What's going on here? All right, so we can see right here, this is our roller coaster. This is the 300 meters over which they're going to speed up, okay? So right now our roller coaster is at rest. Waiting, waiting, waiting. So now we're being put in this back position. And so now there's a magnetic propulsion system that does work on a roller coaster. It exerts a force on a roller coaster over a distance, which causes work. So energy is being transferred from the propulsion system into our roller coaster, giving our roller coaster kinetic energy, and thus allowing our object to move. All right, so try this problem on your own, and if you get stuck, we'll go over here together. So Top Thrill Dragster has a 200 kilogram roller coaster car that can speed up from rest to 52.7 meters per second over the course of 300 meters. What must be the force exerted by a launch system to attain this, okay? So we're going to have 1/2 mvf squared minus 1/2 mvi squared. This is our change in kinetic energy, final kinetic energy minus initial kinetic energy, equals force times distance. In this case, we're not going to have a negative because the force in this case is going to be positive. It's acting in the same direction as our cart is moving, okay? In this case right here, our mass is going to be 200 kilograms. Our initial velocity is going to be 0 meters per second. We start from rest. Our final velocity is going to be 52.7 meters per second. Our distance is going to be 300 meters. So because our initial velocity is 0, we can replace 1/2 mvi squared with just 0 here because our initial kinetic energy will also be 0. So that's going to leave us with 1/2 mass times final velocity squared equals force times distance. So we can now start plugging in numbers. We're going to have 1/2 times 200 times 52.7 squared. Don't forget to square it, okay? Don't forget to square the final velocity, equals F times 300. So as a result, we're going to have 28,000 equals F times 300, or dividing by F, we're going to get, or dividing both sides by 300, we're going to get that the force is 926 newtons. So this is not nearly close to actual statistics, but for hypothetical purposes, it is actually correct, because it turns out there are other many factors that we have to consider here as well. And this is the work energy theorem, our topic for 4.2.